I'm going to talk a little bit about composition of functions in this video. Alright, so what is a composition of functions? It's basically just doing one function, getting a result, and then immediately plugging that result into another function. Alright, so what they do here is they give you two functions, f of x, which is equal to the square root of x, and g of x, which is equal to x squared plus 1, and they define a new function h as f of g of x. So what ends up happening here is it's the same as f of x squared plus 1. So what did you really do here? You just replaced g of x with its definition, right? G of x is x squared plus 1, and then you apply f to that new input, right? So instead of doing f of x, you're now doing f of x squared plus 1. So what is the rule for f? The rule for f is take the square root. But instead of taking the square root of x, I'm now taking the square root of x squared plus 1. Okay, so that would be the definition of a composition of functions, right? You first apply one function and then apply the second function to that result, right? And then what they do is they just give you a visual representation of it with the use of what they call function machines. They say that what a composition is really you're starting with this input x, you're putting it into one function g, you're getting an output x squared plus 1, and then you're immediately taking that output x squared plus 1, putting it into the new function f, and then getting your new output. Right? So instead of doing this in two steps, what you can do is you can bypass that and just do it in a single step, and what you would do is you would call this function f of g. Alright? And here they give you the definition of that, right? So what is f of g of x? It's really just first applying g, getting a result, and then applying f. Okay? So it's a pretty basic thing. And then they just give you another representation of it visually. Right? And again, they show it in two steps, applying g and then applying f, or bypassing that and just doing it in a single step of applying the function f of g. So here's an example. Two functions, f of x equals x squared and g of x equals x minus 3. So we've got a quadratic and a linear function. And now here's something that we didn't talk about before. These two functions, f of g and g of f, they're not the same function, right? F of g, you're first applying g, then you're applying f. G of f, you're first applying f and then applying g. Alright, so that's the first thing they want you to do. They want you to find functions f of g and g of f. So f of g would just be f of g of x, which is going to be f of x minus 3, and then you just square that and you get x minus 3 squared. And realistically, can you leave that in that form? Yeah, because this is what this textbook calls the standard form for a quadratic, right? It's really a times x minus h squared plus k, where a and k just happen to be 0. I'm sorry, a happens to be 1 and k happens to be 0, right? You could just think of the 3 as the h, a is 1 and k is 0, right? So that would be your f of g of x, right? So this is f of g of x, right? That's your rule. And then g of f of x is just the reverse. You first do f of x, which is going to be x squared, and then you apply g to that, so you get x squared minus 3. So it's still a quadratic, but it's not the same quadratic, right? And this would be g of f of x. Okay, and then they talk about domains. Domains we're not really going to get into that much, but the domains of both of these are just all real numbers because they're linear. One's a linear and one's a quadratic. So you can plug in any value of x that you want to there. So you're not going to run into a problem. So there's your two functions. Now, keeping in mind what we just had, for part A, There's our rules for f of g and g of f. Now what they do for b is they actually don't use those definitions. What they do for b is they're trying to evaluate f of g of 5 and g of f of 7. So what they do is, to evaluate f of g of 5 is, they first plug 5 in to g, get a result, and then plug 2 into f, and then get that result, right, of 4. And then for g of f of 7, they first plug 7 into f, get a result, and then plug 49 into g. So what they really are doing here is, they're really doing this in 2 steps. But since what we did in part A gave us new formulas for f of g and g of f, we could have bypassed this and just done this in a single step. So really the easier way to do b would have been to say, alright, well, f of g of 5 is really equal to 5 minus 3 squared, right, using the formula that I got in part A, which is just 2 squared, which is going to be 4, right, which is the same result as they got it, doing it in 2 steps. And then similarly, g of f of 7, if you just do it in a single step, it would have been 7 squared minus 3, which is 49 minus 3, which is going to be 46. So again, I got the same result as they got, but I did it in just one step, right? 46 here and 4 there, right? So to me, the whole idea of getting a new rule for the functions, like we did in part A, is so that you don't have to do part B in 2 steps, right? I think they kind of did part B in a more difficult way here because it wasn't necessary, because we already had new formulas for f of g and g of f, right? So the first, generally, once you have a new formula for the composition, just use the composition. Don't use the individual functions anymore, which is what I did in the way that I did it, okay? All right, and then what they tell you is that in general, f of g is not the same as g of f, as it wasn't in those cases, right? In one case we had the quantity x minus 3 squared, in the other case we had x squared minus 3. All right, and just remember what the notation means, right? F of g means that you're applying g first, and then you're applying f, whereas g of f is the reverse. Okay, and then they tell you that you can apply more than you can take the composition of more than 2 functions. Generally, we won't do that, but you can. I mean, you can take the composition of as many functions as you want to. All right. They give you an example of that, but I'm not going to really worry about that. I mean, you can look at that on your own if you wish. All right. Now, a lot of times what's useful to do is to take a single function, and instead of taking the composition of it, do what they call decomposition, which means you're going to break it up into 2 or more simpler functions, right? So this is just the reverse, really, of what we were doing before. So if you look at something like this, capital F of x is the the fourth root of x plus 9. Think about what's going on there. There's 2 things that's going on, right? What are you doing first? You're first taking your input x and you're adding 9 to it, and then you're taking the fourth root of that. So I can break this up into 2 simpler functions, one being x plus 9 and the other being the fourth root of x. And the only thing that you have to be aware of here is order, again, right? Because we said that in general f of g and g of f are not the same function. So just think about what was done first here. So first you're adding, and then second you were taking the fourth root. So if you're calling g of x x plus 9 and f of x the fourth root of x, and you want to do x plus 9 first, you're doing g first. So you're really doing f of g of x, right? Because what would f of g of x be? They're probably going to do it on the next slide, I would think. Yeah, right? F of g of x would be f of x plus 9, and then you're taking the fourth root of that, which is your capital F function. Okay? Do one more of these. Suppose you had a function capital G of x that was something like (2 over x minus 5 squared). Now what you'll do here, maybe, what you might do here is you might look at this and say, oh, well, there's three things being done. So I could write this as the composition of three functions. True, you could, but it's probably easier just to write this as two functions, right? So you could actually even write this as the composition of four functions, I believe. But we'll try to do it in two functions. So just think about what's happening here. There's really three things that are happening here. First, you would be subtracting 5. Then you would be squaring. And then you would be dividing that result. Well, you'd be doing 2 divided by that result. So that would be the third thing that you would be doing. So what you can do here is you can combine 2 of those steps into one if you want to. So rather than just write it as 3 separate functions, what I can do is I can combine the first and second into one function where I subtracted 5 n squared. So I can think of one function, let's call it f, lowercase f, as subtracting 5 and then squaring, which would be x minus 5 squared. So what I did is I took the first and second steps and combined them into one step. And then the second function would have been taking 2 and dividing my input by that, which is x. Right? So I would have applied lowercase f first, and then I would have applied lowercase g second. So let's just check and make sure that if I apply lowercase f first and lowercase g second, which would have been g of f of x, I get g of f of x, which is really going to be g of x minus 5 squared. And what is g of x minus 5 squared? Well, g is 2 over x, so I'm replacing x with x minus 5 squared, and I end up with 2 over x minus 5 squared, and that is indeed my capital G function. Right? Because this is the same as what I started with here. Right? So if I use lowercase f as quantity x minus 5 squared and lowercase g as 2 over x and compose them, I get my capital G function. So that's just another example of what you would call decomposition. And again, realize that I could have, decomposed that if I wanted to into even 3 functions. Okay? And technically 4 functions. I could have called one x minus 5, the other one x squared, another one 1 over x, and then another one 2x. Right? So I could have went as far as actually decomposing that into 4 functions. But I think 3 would have been more likely. But here we did it with 2. Okay? And that's going to be important for calculus, to think of one big function as a series of smaller functions.